Okay, part 2 of the problem asks you to find the minimum radius of curvature at position 3. Okay, minimum radius of curvature. As in, okay, let's say you're the design engineer. You have this this roller coaster track right here. Right? So you can design it to be very sharp like this, okay, or very flat like this too. Okay, at position 3. Right? So the minimum radius of curvature is when this is very, very curved. Okay, so that the radius of curvature right here, okay, is small. Okay, compared to this very flat case where radius of curvature is huge. Right. So we asked to find this minimum acceptable radius of curvature at position 3. Okay, so that the car would not fly off. Okay, and of course, imagine that if you design this track to be very, very sharp, okay, extremely curved like this, right? Imagine you're sitting on this roller coaster right here. What happens when you're traveling at high speed, right? When you arrive at this position, okay, it's going to tend to go off, right? So this is a sort of concern with safety of the roller coaster track, right? So the minimum acceptable radius of curvature at this position, okay, what is that? And how do you find that? Well, first of all, you're asked to find radius of curvature. So that means that immediately you should be thinking in terms of tangent normal coordinate system, right? So rho appears in the normal component of the acceleration, alright, and Newton's second law. Okay. Second of all, we need to find rho, okay, which means that, okay, again, if you look at this right here, this normal component of acceleration equals v squared over rho. Right? So that means that you need to somehow find v squared, okay, or v at this position 3. Right? So find v3, okay, and you can know this normal acceleration, then you can find your radius of curvature. Okay. How do you find V3? Well, again, velocities involved here, just like first part of the problem, right? Work energy method could be most useful. So let's apply that, right? And apply work energy equation, okay? Change in energy equals work done before, after. Okay, so before, right, I can choose position 2 as the before, and then after is position 3. I can do that, no problem. Okay, I can also change the initial position to position 1 if I like. Okay, so I'm really concerned with these 2 points, 1 to 3, that's all. I'm not concerned with anything in between. Okay? Position 2, I don't care about. Okay? So I can do it at 2. Now, the advantage of choosing position 1 as the initial position is that velocity is 0. Okay? So the kinetic energy term goes to 0 right away. So kinetic energy 3 minus KE1 equals, again, forces dotted with yes, going from 1 to 3. Okay. This, you know, goes to 0. So the only term to survive on the left-hand side, 1/2 mv3 squared equals, now right-hand side, m0 as before. Right? This is the only force that does work. Okay, going from 1 to 3. And the only force that does work here is weight, okay, or weight vector. So take the dot product, okay, between the weight and the change of position ds vector, right? The dot product again means that it's projection of one factor onto the other, right? And then you take the value of these two vectors, modify them together. So the first vector here, or the magnitude of the first vector is the weight times the change in height, right? Since weight is in vertical direction. So change in height between 1 and 3, which is 1 and 3. So it's this delta z 1, 3 right here, okay? Which is 40 minus 15. Okay? So 40 feet minus 15 feet. Okay, that's all. So let's keep going. Now V3 is the unknown, right? So keep it as V3 squared, right? And then this mass, you know, mass is, you just write this right away. Weight divided by G. Weight and weight again disappear. They cancel out. So 2G times, this is 25 feet. So this is 50 times G. Okay? So V3 squared equals 50G. Now I'm going to keep it as V3 squared. I'm not going to solve for V3, okay? Because I'm not interested in knowing what the velocity is. Okay? I'm going to use this to find my radius of curvature rho. Okay? So keep this as it is. Okay? Because this is precise. Exactly 50 times G. So we're going to keep going. Now to find rho, now I need to use second law. Okay, for position 3. So I'm going to draw the free body diagram at position 3 and kinetic diagram. Free body diagram at this position, I have weight. Okay. Now at this position, I have normal force. And that's it. No other forces. Okay. The kinetic diagram at this position, again, it's traveling on a curve, so you have MA tangent and then MA normal. But since this is at the top of the curve, once again, this acceleration term, okay, which is dv dt, again is 0. Okay? So the only term to survive here is an, which is v squared over rho. V3 squared over rho. Okay, let's put it together into Newton's second law. Okay, apply in the normal direction. Okay, in this case, it's same as the vertical direction. And since I have the normal component of acceleration pointing downward, okay, so it may be more convenient if I define my positive pointing down. Okay, you can choose the opposite if you like. Okay, it's the same thing. So left hand side is weight minus normal force equals ma, which is this right here, and that's positive, right? This positive going downward. So m is weight divided by G times A, which is V3 squared over rho. Okay, so now I arrive at this equation. I want to find the minimum rho. When is this minimum? When is my rho minimum? This is minimum, okay, when this whole term is the maximum, because this appears in the denominator, right? So rho is minimum, making it the maximum value for this and left-hand side.